So in class, we played with a lot of the transformations that we could do to our exponential functions and saw how they changed all of the features that we saw in the previous video, our domain, our range, our asymptote, our y-intercept. But now we're going to get a definition of what an exponential function is. And it does vary a little bit. Some of those transformations can't be written in this format. Only one, all the other ones can, but that one cannot be written in this format. So what we mean by an exponential function in this definition is something that has that pattern that we saw in the table. Something where we can actually see that repeated multiplication in the table. And anything that violates that is going to be a problem, and we're not going to call it, even though it's an exponential function as its parent and we've transformed it, it doesn't get to fall into this nice pretty thing and get all of these cute bullet points that follow. So, oops, I said function, repeated multiplication. So let's look at this from the standpoint of before we even plug anything in. Let's just leave this as a times b to the x and see what the resulting table looks like and see that pattern. So let's just start our table, x, and then our function is a times b to the x. As a reminder, the x only applies to the b. It's the only thing it's touching. If it was applying to both, we'd have them in parentheses. So as we discussed in class, this would be a vertical stretch. It's happening to the outside of our parent function. That a, we're doing a vertical stretch by a. But you don't see that wording anywhere in the bullets. So let's just plug in and see what happens, see that pattern. So I'll go ahead, 0, 1, 2, 3. I'm going to start with 0 and then move down. So if we plug in 0, we'll get a times b to the 0. And we know anything raised to the 0 power is 1, so this is just a. Then we'll get a times b to the 1, which is just ab. A times b squared, which I mean, kind of silly that I'm writing it as a separate thing. And then we'll get ab cubed. So again, the idea here is that we can see this repeated multiplication. As we move in this direction, each time we're taking the previous answer and we're just multiplying by b as we increase our x by 1. So we're basically saying in words, a times this many b's, right? And so we can see this first bullet point in action. Our first bullet point says a is a non-zero real number. It's called the initial value. So here, this is what they mean by initial value, right? It's where we started from. And we can also get the last bullet point here. We are going to get a y, on part of the last bullet point, we're going to get our y-intercept at 0, comma a. We can see that right there in that highlighted piece. And we can also move in the other direction using our pattern. If we're multiplying by b each time, the opposite of that is dividing by b. So without actually doing the math here and showing our reciprocal, this is going to be a over b. Then we'll get a over b squared, a over b cubed. And hopefully we also see this idea that we're getting really close to 0 because we're going to be dividing a by some gigantic number by the end, right? We're basically going to have a divided by infinity as x goes to infinity. We're not allowed to write that. But that's what's going to be happening, which is basically 0, but not really 0. There's still a tiny bit of something left. So that's where we get that horizontal asymptote and that end behavior that we talked about in the previous graph. So let's look at other pieces of these bullet points and see what else we have here. So other pieces of the bullet points that we can talk about, b, of course, has to be a positive real number that isn't 1. What happens if it is 1, of course, is that we would just have f of x is, right, like you should always ask like the what if. Like what if it's equal to 1? Well, then we just have that our f of x is equal to a times nothing, right? 1 raised to the power is 1. So that would just be a straight line. It wouldn't have these cool properties, right? It wouldn't have what we're hoping to see when we look at an exponential graph, or what we know we will see when we look at an exponential graph of this, sort of look of the graph where one side is going off towards 0 and the other side's going off towards, in this case, infinity. We also need it to be positive because if it's negative, like you could just say, well, what if it's negative? And let's just choose the easiest negative. We'll choose b is equal to, let's do -2 because we've been dealing with 2 as our base. If we did that, we could make a quick table. Let's just make a1. So we'll make life really easy here. We'll just say, what if this was the case? We plugged in 0. Oops, I need parentheses, otherwise that negative is on the outside. The x would only be applying to the 2. This would be 1. We plug in 1, we get -2. We plug in 2, we'd get 4 because a negative times a negative is positive. And you can kind of see the problem here, right? We're all up, we're not getting this pretty continuous graph. We're jumping above and below the x-axis. We're going to be positive whenever our x is even. We're going to be negative whenever our x is odd. And that doesn't even deal with what happens if we plugged in, right? If we had our x and we tried to evaluate at a fraction, right? If we try to evaluate at 1/2, this is just a fancy pants way to write the square root, which is not a real number. So we're going to have giant chunks missing from our graph. Like this is just a hot mess. I don't even know what it would look like in Desmos. So we cannot plug in negatives and we cannot plug in 1 as our b. Our base has to be some positive real number, non-zero, non-1. If this is true, then of course we get our domain out of negative infinity to infinity, as we discussed, right? I can plug in anything as a exponent. And then our range, here we see something new. Our range, when we were looking at it, was always about positive reals, right? Starting at that asymptote and moving above it. But if our a is negative, what'll happen with an a if it's negative, this last bullet point, is that we're going to end up with think about our transformations, a reflection over the y-axis. So we're going to see something like this that is not nearly exponential enough. Let me make this thing look a little more exponential on this high end. We're going to see whoop, something like that, where as our end behavior, right, as x is going to infinity, our f of x or our y is going to negative infinity. So in this case, we would be taking all of our values that we got out here in the right side of that table and multiplying them by a negative, which would mean that we're going to get as close as we can to 0 still, but we're going to end up with very big negatives on the other side. So that's that. Let us look at this cool example because I want us to notice that almost all of our transformations that I was saying can be thought of or written in this format. So this first bullet point is the one I want to look at because this first bullet point, we have a horizontal shift, and we have a horizontal compression, right? A shrink by that 3. So everything is happening inside. It's happening to the x's. And since it's all happening to the x's, what's going to be true is it's not going to impact the output. We're still going to preserve that repeated multiplication. In fact, you could go ahead and make yourself a table to see. We got x, 4, 3, x minus 2. We could plug in 0. That's going to give me x to the negative, or 4 to the negative 6. I don't know what the heck that is. It's something real small. Plug in 1, I'm going to get 4 to the, what's happening here? If I plug in 1, I'm going to get a negative 1, so that's going to be negative 3. I plug in 2, I'm going to get 4 to the 3. I plug in 3, I'm going to get, oh, I'm insane. This is 4 to the 0. Sorry. That should have been 1. And then this will be 4 to the 3. So it's a little bit harder to see when things are in the exponential format, but there is a repeated multiplication here. Each time as we move, we are multiplying by 4 to the third power. 4 to the third power, 4 to the third power, and we're adding that exponent. So it is not changing that rule, that repeated multiplication rule. And so what I'd like us to see is how we can rewrite it so that it matches our yellow thing, our format of the a times b to the x. So we need a little bit of exponent rules. First thing we'd want to do is distribute out that 3, which I don't think is necessarily an exponent rule, but more of a just, basic math rule. So we can do that. And then what we're going to do is something we don't typically do, but you will have to get comfortable doing because we do this a lot, especially when you're in Calc 2 and you're messing around with the geometric series that we're going to see at the end of this semester. But we want to rewrite this as 4 to the 3x times 4 to the negative 6. And so here is where things get funky. Most students are used to going in this direction. They're used to seeing, oh, two things, same base, I can add their exponents. And they're not as comfortable moving in this direction to recognize that if I have something to a power with addition or subtraction between the terms, I can rewrite it as two things to that same base, either multiplied or divided. So I'm going with multiplication because, again, my goal here is to make this a times b to the x. So I want nice little pretty thing. So there we are. Okay. Now it's still not perfect, right? I could definitely rewrite this. I've got a 4 to the negative 6, and I've got that out in front. That's my a term. I can already see that. And it makes sense when we look back at this thing. We've got my initial value, so this piece all makes sense. But this piece is not matching yet, this 3 to the x, because there's only an x in the b term, right? This has the vertical stretch in it, and I need to rewrite it without any of those transformations. Like, that's the goal. So what I can do is use a different exponent property, this one again that we typically don't write in this format. I'm just going to do this piece. This is equal to 4 to the third. Oops, don't like how that 3 looks. 4 to the third raised to the x power. So again, we typically do this in the other direction in an algebra class. We go, okay, something raised to an exponent raised to another exponent, I can just multiply, and we don't do this piece as much, where we go from the multiplied back to these two chunks. I don't like that, it looks ugly. So, but now I can rewrite this. I'm completely done. This is now 4 to the negative 6 times, that's 64, 64 to the x. So now I have an A and a B, and I'm done. I've got everything. It has a very steep B, right? We've got this giant base. We're multiplying each time by 64, or 4 to the third, and we've got our initial value. So we can also see that repeated multiplication value in the table. That's my base. And again, that initial point, that's my A, that 4 to the negative 6. So vertical stretch, no, horizontal shrink, sorry, horizontal shrink, and our um, horizontal shift can both be written in this format. They can both be manipulated. And we talked about this a little bit when we did it too. A lot of times a vertical stretch and a horizontal shrink, they're two sides of the same coin for many, many functions. And so it's all about rewriting them and which way you're going to be looking at the values. So that's sort of the rewriting. There's some really cool questions in Delta Math about rewriting things in different formats back into this a times b to the x, into this format that we're sort of used to, that carries so much meaning, especially in our like application context questions.